What is up, amigos? Today we're looking at the ideal gas and what it is and some requirements for it. So the ideal gas is very important in aerodynamics, and we'll be looking at it from an aerodynamics point of view. So what is it? So let's say we have a gas and there are all these particles around. So the ideal gas follows this equation. P equals rho RT. This is pressure. This is density. This is the gas constant of the gas here, and this is the temperature. So this is in pascals, this is in kilograms per meter cubed, this is in joules per kilogram per Kelvin, and this is in Kelvin. So the ideal gas equation will only hold if these particles do not interact with each other, so they don't hit each other. And that's pretty difficult because pretty much all gases, the particles do move around. They have different kinetic energies and they're on different paths, so they will collide and go away. So technically nothing is really an ideal gas in real life, but we can still use the ideal gas equation if something holds true, and that is if when two particles collide, the amount of kinetic energy in the system doesn't change. So the kinetic energy doesn't go into noise, it doesn't go into potential energy, it just stays as kinetic energy. And for a gas such as air, this is actually a pretty good approximation. So we can actually use the ideal gas equation for air and still get a good relationship here. It will hold quite well. And this is because these particles in air, when they collide, they don't really change their kinetic energy into other forms of energy. It just stays as kinetic energy in the system. So let's go through what this equation means. So let's say on a regular day, I'm saying that today is 20 degrees Celsius, which equals 293.15 Kelvin. And the density is 1.2 kilograms per meter cube. This is not strictly true, but let's just assume that because this is what everyone assumes, like we always assume 1.2, 1.225. It does change though. We're going to say this. And the gas constant is 287.05 joules per kilogram Kelvin. So if we were to plug this into this equation, P equals 1.2 times 287.05 times 293.15, we actually get the pressure here is 100,926 pascals. So that's pretty close. So when we talk about the barometric pressure in the atmosphere, like when we're walking around, we often assume that the pressure equals 101,300 pascals. So this is actually very close to what we've calculated here, assuming an average day's temperature and an average density. So that's how we can use this ideal gas equation to figure out what other properties are. Or if, for example, we measure the pressure, the barometric pressure, and we know the density, or we calculate it and we know the gas constant, we can calculate temperature, or vice versa. Any of these properties in here, as long as we know three, we can find out the other one. And this is what the ideal gas is. And for the noble gases, it holds true very well, as it does with air. Now, one thing I should note is that this equation does break down a little bit once you start talking about the humidity, the relative humidity. When you put more water into the system, this starts to break down, and when you reduce it, this is all assuming dry air. So this R here is for dry air, and then this density we also sort of calculated for dry air as well. Anyway, that is ideal gas. And if you want to learn more about this, check out our other videos and our course link in the description for aerodynamics fundamentals. And check out a book by John D. Anderson called Fundamentals of Aerodynamics, also linked in the description. So like this and subscribe. Peace out, amigos.